Hello, this is a little help on Lab 8, Universe of Galaxies and Dark Matter. Part 1 is about the Hubble classification sequence for galaxies. And you need to read the introductory paragraph and these paragraphs here and study this tuning fork diagram. Galaxies are classified according to whether they are ellipticals, indicated by letter E, or spirals, indicated by letter S, or barred spirals, indicated by SB. And they're asking you to simply look at the 6 galaxies and classify them. Write down your classifications here. Now in part 8.3 of the lab, we're going to investigate dark matter in this galaxy, NGC 2742. What is dark matter? Nobody knows, but we know it's there. It's not luminous. It's not like stars or glowing gas, but it affects the rotation speed of all the stars and gas in the galaxy. Think back to the Jupiter's Moons lab that we did, and remember Kepler's third law, or Newton's form of Kepler's third law in particular, tells us that if we have a high mass at the center with things orbiting around it, if we have information on the rotation period and the distance of those things orbiting around that central mass, we can calculate the central mass. Well, here we have a rotation curve, which is based on what we can observe in this galaxy, which is on the horizontal axis, the radius from the center in kiloparsecs, thousands of parsecs from the center, and then the radial velocity, that is the speed of the gas that's observed by Doppler shifts, corresponding to these different distances from the center. Now, since the speed of motion is related to the period of revolution, Kepler's third law, Newton's form of Kepler's third law, will work and allow us to calculate the mass which is interior to each of these distances where we have reliable radial velocity data. Okay, so now that we understand the rotation curve, the first step is to find the radii listed in the first column of Table 1. So here is Table 1, and the radii are listed in the first column. And we are going to record the corresponding radial velocity values in column 2. Try to be as precise as possible. So I have this one, for example, 3 kiloparsec radius. Drawing a line across, I get 125 plus 1 tick mark is another 5, so that's 130 kilometers per second, and I put 130 kilometers per second in this column here. So do that for everything in that column. Okay, the next step is going to be to fill in the total mass column using values you calculate from these numbers here. The formula here is given. We are going to square V, which is the 130, multiply it by R, which is the 3.0, and if you examine the units that this G is given in, the number you divide by, G is a constant of nature, and the units they give it in indicate that V is in kilometers per second, R is in kiloparsecs, and when you cancel everything with these given units of G, the answer comes out in solar masses. So that's how you know to put in V in kilometers per second here, just as it's written, and put in R in kiloparsecs, just as it's written. Now let's look at a sample calculation using those numbers, and here they are. We're just interested in down to here. 130 squared times 3 kiloparsecs, and you divide by 4.31 times 10 to the negative 6 for G. This will be the same number in all the calculations. Always divide by this number. And for this one, we come out with the mass total, m sub t, equals 1.18 times 10 to the 10th solar masses. So I want to put that in my table 1, 1.18 times 10 to the 10th solar masses. On the calculator, here is how we're going to put that in. This is a TI-30X calculator, and there we go. I'd like to point out a couple of convenient features to this calculator. One is that you can put it into scientific or floating point mode. Scientific mode means the answer comes out in scientific notation. If I wanted it in floating point mode, I would select that one there. Let's take a look at the answer in scientific notation here. Enter that. And another feature of this calculator which is convenient is that you have a fix function. I can do second and fix, and I can indicate how it's going to round it off following the decimal point. So this will round it off to 3 after the decimal point. So I simply put in 130, and I need to square that number, so I press x squared, and then I go times, and then I need to put in 3, and then I need to divide, and to be safe I'm going to put this denominator in parentheses, 4.31 times 10 to the negative 6. Now here's another feature of the calculator. Pressing the second key, EE, gives me scientific notation mode, and I need negative 6. Now this is the negative key down here, different from the subtraction key. Negative 6, end parentheses, and equals. And here comes the number out in scientific notation, 1.17 times 10 to the 10th. Okay, page 68. Now that you've determined the mass of the galaxy that's interior to each radial distance, based on the gravitational influence of the mass, let's find out how much of that mass is actually glowing, and then that lets us calculate how much of it is dark matter. So this is a graph. This figure 4 is a graph. Again, radius from the center on the horizontal axis in kiloparsecs. On the vertical axis, we have light interior to that radius in solar luminosity units, L sub r for light interior to that particular radius. So how bright is the galaxy inside of 3 kiloparsecs here? I read across and I read off 1.1 times 10 to the 9th solar luminosity units. So I'm going to write that down in the next column in table 1, 1.1 times 10 to the 9th solar luminosity units. And you may be wondering about this last one here. Notice that this number is simply 2 times this number, and that's because they say here, if you read this paragraph, they explain that statistics on stars show that for every solar luminosity unit of just a bunch of random stars, there's about 2 solar masses that are responsible for that much light. So they want you to very simply multiply by 2, multiply this number by 2 to fill in this column here. Question 2. Question 1 was the Hubble classification system. Question 2. Consider the farthest point from the center of the galaxy. What percentage of the total mass of NGC 2742 is luminous, or in other words, contained within stars and gas? What percentage of the total mass cannot be accounted for in the light observed? Well, you have in your table that you've been filling in, you have the luminous mass in this column, and you have the total mass in this column. So the total mass, of course, is greater than the luminous mass. So if you divide the luminous mass by the total mass, and then multiply by 100%, you'll get that percentage. And here's the calculation. The percent that is luminous is 2.2 times 10 to the 9th solar masses, divided by 1.18 times 10 to the 10th solar masses, times 100%, gives us 18.6% luminous mass for this particular distance. Now the instruction says, consider the furthest point from the center of the galaxy. So that's what they want you to consider. So I haven't given you the numbers. You find those numbers yourself. So you're working with this number here and this number here. That's the farthest point from the center of the galaxy. So you want to calculate a number different than mine for the ratio of luminous to non-luminous mass. To find the percentage that's dark matter, you would simply subtract your percentage from 100. So for example, at 3 kiloparsecs, the percentage that is dark matter is 100 minus 18.6. Based on this, number 3, is there evidence for the existence of dark matter in NGC 2742? Clearly explain your answer. Let you do that on your own. Using the blank graph on the last page, plot the total mass as calculated from the rotation curve. So that's total mass here in that second column, or is it it's the third column actually, sorry. This column here, total mass versus radius. And then do the same for the luminous mass versus radius. The luminous mass is in this column here. Now let's take a look at that table, or at that graph, the blank graph. First I want to label my axes. The vertical axis is mass in solar masses. The horizontal axis is radius in kiloparsecs. And the title, I'm going to put a title on here. Graphs should have titles. Total mass and luminous mass versus radius for NGC 2742. For my first point, I'm going to plot the total mass at 3 kiloparsecs. And you can see I put a ruler down, and this thing won't focus unless I get my hand out of there. I put my ruler down and read off the value 1.18 times 10 to the 10th and 3 kiloparsecs, and so I'm going to put a point right there. And for the other value, its luminous mass is 2.2 times 10 to the 9th, and on here 2.2 times 10 to the 9th would be just 2/10 of this 2.2, each of these is 2 times 10 to the 9th, or each of these is 1 times 10 to the 9th. So 2.2 times 10 to the 9th would be right about, let me just indicate it with my pencil here. This is 1 times 10 to the 9th. And so, see, this is 1/10 of 1 times 10 to the 10th. So this is 1 times 10 to the 9th. So 2.2 times 10 to the 9th would be right about here. So notice that 0 is right here. They give you a couple of points below 0 for some reason. So you could very carefully lay your ruler down, as I'm showing you, and you'd line it up with the marks on both sides for the greatest accuracy. You understand? So here's 0, 1, 2, and a scotch, and connecting that, make a point there. And there's my point for the luminous matter. And you may want to use a different symbol. Maybe I will use an open square for luminous matter and a dot for total matter. Alright, on page 70 we're going to be calculating the distribution of matter by looking at the slope on our graph for 3 different regions of the galaxy, for the nucleus, the disk, and the halo. So let's just look at the nucleus for an example, 1.0 to 3.0 kiloparsecs, and we're going to calculate the luminous mass slope. And the slope is rise over run, remember from algebra class. And for the purposes of this exercise, I went and I calculated the 1.0, read the radial velocity off, calculated the total mass, read the luminosity off, and doubled it. So I have the luminous mass and the total mass, and for 1 kiloparsec, and I'm going to plot that on my plot. And I did that here, and I also plotted the this is the total mass here between the solid points, and here's the luminous mass between the two squares. And slope calculation example here is the slope from this point to this point. So this is the inner core of the galaxy. They call it the nucleus. The nucleus is this range in here, and the what is it now? The disk is 4 to 7, so out to 7. This is the disk out here from 4 to 7, and then this is the halo out here from 8 to 10 kiloparsecs. So for the slope for the nucleus here, I calculate rise over run. The rise is the difference between the mass, that is, of this point and the mass of this point. So you can get that by simply subtracting this mass minus this mass. That gives you the rise. So that's this calculation here. This is the numerator, rise. This number minus that number, 1.18 times 10 to the 10th minus 2.01 times 10 to the 9th. And then divided by the run. The run is simply from 1 to 3 kiloparsecs. So it's 3 minus 1 is put down here in the sense of this minus this. So I have calculated, subtracted here, got 9.78 times 10 to the 9th. Divide by 2, and I get 4.90 times 10 to the 9th, and the units are solar masses per kiloparsec. And I want to put that in the table right here for the total mass slope. Now you're going to calculate the slope also for the luminous mass in the nucleus, and then again for the disk and the halo for both luminous and total masses. Final questions. What do the different slopes tell us about where mass is distributed? Is it evenly distributed, or are the two types of mass, luminous and total mass, concentrated in different parts of the galaxy? So read the rest of that question, read this question, answer the questions, and you're done. Thank you for listening. That was a little help on how to do lab number 8, Universe of Galaxies and Dark Matter.